Right, ladies, gentlemen, thank you very much indeed. Plenty of room up front, as my headmaster used to say, for those who want to come and get closer to the action. Very good. So welcome, everybody. My name is John McGrath, and I'm the academic head of St. John's Institute of Dermatology. It's my pleasure to be helping chair this evening. They have given me a script to try and follow. I think that's right, but I'm notorious for going off script, I think, aren't I really? But this is not really about me. It's not really about the staff tonight. It's about you. It's about patients. It's about public. It's about telling you something about the work that we do in looking after patients with skin diseases. So welcome, everybody, to this special event tonight. Plenty of room up front. Please make your way down to the... Fantastic. So it says, I should welcome you to what we're calling Skin Health, Celebrating New Advances. And this is a presentation by St. John's DermAcademy in partnership with King's Health Partners. This is actually the very first in what will be a series of in-person conference events, patients and the public. And I join with the rest of St. John's in welcoming you this evening. I think most of you know St. John's as it is right now, but just very briefly, St. John's has been around for about 160 years. It was actually founded not by a physician, but by a surgeon who had hand eczema and who couldn't operate and needed to do something else. So we owe our origins to a surgeon, so somehow those surgeons are still important to us. And we've been in various places around London: Trafalgar Square, Leicester Square, Homerton Hospital, St. Thomas's Hospital, and now here we are for the last 15 years or so at Guy's Hospital. And we're a department that provides an arrangement of clinical services and also underpinned by a lot of research. And what you're going to hear about tonight is some of our research that's making a difference, the new advances where we're taking research literally from bench to bedside. And so what do we do in St. John's? Well, you'll hear that in the topics that we cover, but we're interested in all types of skin disease. We see tens of thousands of patients every year in our outpatient services with inflammatory diseases like eczema, like psoriasis in children and in adults. We see allergies, we see different types of inflammation, we see blistering diseases, genetic diseases. We see a whole range of conditions that you will hear about tonight, including skin cancer and some of the other new therapies that we're developing for patients, many of which some of you will be familiar with tonight. So a great pleasure to bring our St. John's, our modern St. John's, to you this evening in this presentation of various skin diseases. And so let us get on with our first speaker this evening. So this is Sophia Karagiannis, who is an allergo-oncologist, an immuno-oncologist. She is interested in your immune cells and how they impact on cancer and how she can develop new therapies to target some of those diseases, those cancerous diseases for which new treatments are so desperately needed. I won't eat into her time, so Sophia, over to you for your work on skin cancer. Sophia Karagiannis, thank you.
For inviting me, and thank you all for coming to join us tonight. I'm really delighted to be here and to share with you some of the work that we're doing and some of the things that keeps us motivated to find treatments for patients with skin cancer and other solid tumors. I have a background in immunology and in allergy, but I use that information to study cancer, and I also bring along knowledge on innovation and work in the private sector in pharma and biotech, where I did my training and my early years of postdoc. And I bring that on board so that we can always focus on what really matters, is to develop therapies and how do we use to study the immune system to make more effective and more efficacious therapies. So we always start with a challenge, and the challenge is we have melanoma that has been for many years difficult to treat, but in the last 15 years things have changed. Knowledge of the immune system has made a difference we have now used that knowledge to develop therapies that actually make a difference for patients. But for many years, a lot of immunologists like me got very fascinated with cases like this. It's a melanoma that in the middle has been reduced, and that reduction, that destruction of melanoma comes from the patient's immune system, which can be seen inside a cross-section of a tumor here. You can see immune cells coming into the tumor. So if we can understand those immune cells, we can develop therapies that can activate them. And here I'm just showing you what people for many years have been looking to try to understand how cancer cells differ from healthy cells. And these are 10 ways by which to do, and I've highlighted 2 of them. They hijack the normal inflammation process and how we activate our immune system and then switch it off when an infection is cleared. And they also manage to take this process and hide from the immune system so they can grow without the immune system destroying them. We have a constant immune surveillance in our body that destroys any cells that have gone wrong. In cancer, some of these processes go wrong, and the cancer cells can switch off these immune processes. And we try to understand that, because when we do, we'll be able to make therapies. And I'm showing you here an example of this. This is what we call immunotherapy now. They are antibodies that are made in the lab. They can target and switch on T cells, which is a type of immune cell. And when they do that, they take the brake off the cells, and these cells go crazy, and they will kill cancer cells. And this has developed into very significant survival advantage. This is the classic chemotherapy for melanoma, using a drug called dacarbazine, and this is using the novel immunotherapy, and you can see how many more people survive melanoma now by giving this type of therapy. However, I will show you that we have a problem. We haven't cured cancer yet. We have improved the outcomes, and we can do so much better. This is something that motivated me from the moment that I started working in the private sector, because they look at money and I didn't, but this made a difference for me. This is the % of drugs that go from the moment that they are approved to go into a clinical trial until they actually are accepted by the regulator to be given to patients. And we're talking about 5% success. To me, that's not good enough. 5% success. Look at how it's happening in cardiovascular. They are much more successful in getting their drugs approved from the moment that they go into a trial. Can we improve that? And the way to improve it for me is to try to understand what's happening in the tumor. How can we understand those mechanisms there? And then how can we use these vulnerabilities that reveal themselves when we study cancer to develop better treatments? So when one looks at a tumor, we're not just looking at the cancer cells. We're looking at an array of other cells around them, including stromal cells that provide the bedrock for the cancer to grow, the normal cells that the tumor hijacks to allow it to grow. But also there are other cells there, such as, and I'm highlighting some of them here that interest our group. One of them is B cell. B cells are our natural antibody factories in the body, and they're actually recruited in the tumor, and they're changed in the tumor context. How do we understand that, to understand why our natural antibody-producing cells are not producing the right types of antibodies? What can we learn from that? And there are other cells like what we call macrophages. They're there to clear anything that looks wrong, to destroy cancer cells, and antibodies actually can engage those cells, and they can direct them against the cancer cells to kill them. And in our lab, we're trying to understand how that happens. Our immune system makes 9 different types of antibodies. So our B cells in our body makes 9 different types of antibodies to help us to fight infection. Here I'm showing you 4 of them. We know very well that we can make these in the lab ourselves, and we can study them. But we know that in the body, one of them is very active. It activates in the immune system really strongly. And one of them is not very active at all. Our immune system makes it when it wants to stop activation. Cancer cells actually support the presence of B cells that produce antibodies of this type, the less activating ones. And in fact, we found that patients who have these high levels of these abnormal or switched off antibodies in the blood do worse in terms of survival, even without treatment, compared to those who have normal-like levels of these switched off antibodies in the blood. And we find that certain types of B cells, which are regulatory, they're switching off our immune system, are actually favored sometimes. And we can see that if we have those antibodies, these patients don't respond very well to therapy, here immunotherapy. We find that these antibodies, when they're enhanced in the blood, the patients who receive immunotherapy don't do very well. So we know there are mechanisms there that can tell us even at early point how the patient is going to do. And they are relating to the type of immune response that we can measure and understand in the patient, either in the tumor or in the blood. We can tell that an antibody presence there, the type of antibody that's there, can predict whether the patient will do well without even treatment. And we can tell that this antibody, if it's there, the patient will do well even in the presence of treatment. But our immune system, I mentioned, makes 9 different antibodies types in the blood. But only one of them has been used for therapy, and mostly people use this activatory one called IgG1. Yet a lot of them don't work very well in the tumor microenvironment. So we reasoned that we can look at other types. Our immune system doesn't use one type to survive, to do well. Doesn't use one type to protect us from infections and from pathogens. So can we look at different types? And in fact, some of them work very well in tissues, including in the skin. And one of them is called IgE. And we have shown that actually, here is the cancer cell that is green, and this is an immune cell that is red. When we add this antibody, the tumor cells are starting to be pulled apart by the immune cells here. You can see the immune cells are starting to ingest this green material that comes from the cancer cells, and the cancer cells are starting to die. So we know that in the lab, we can make a special antibody that can overcome all these regulatory and suppressive mechanisms and can work even in the context of this suppressive, immune suppressive environment in the cancer. And I'll show you here 2 slides to see live how cancer cells are dying in the presence of the right antibody. On the left, we have an antibody that we generated in the lab that can activate the immune system. Cancer cells are in green, and when they lose their fluorescence, the green fluorescence, it means they're dying. And some of them, they absorb a red fluorescence, which we put in the supernatant, and they take it in when they're completely dead. And you can see on the left here, I will try to help, hopefully, you can see the green cells are dying, and they're absorbing red dye. That means they're losing their fluorescence, they're time to die, and then they absorb the red dye, which means they're completely dead. They've lost their membrane integrity. And you can see what happens when we put an antibody there that actually doesn't recognize cancer cells, and nothing happens. Green, happy green cells. So we can show in the lab that we can destroy cancer cells in the Petri dish, in the lab, in the test tube, using the right type of antibody. And we've actually taken it to an animal model, and in this case, I'm showing you an antibody here, and this graph is a survival. So the longer this graph goes out, the more these animals survived after being given a treatment. And you can see, given our drug here, that animals survive longer, but given another type of drug, the classic one that people use in therapy, the animals die, and all the other controls are here, which means our drug can improve survival of mice in the lab. We can show that the tumors that grow in the lungs of the animals in white dots, when we do the right treatment, you can see lack of dots, which means the tumor hasn't populated the lung. We can show that the tumor in melanoma doesn't grow very well when we add our antibody or special antibody. When we use the classic antibody, the tumors still grow a little bit, and you can see so the controls are even, tumors are growing very high. This is a patient-derived model from patients with cancer, with the patient's immune cells included, and you can see the animals survive better when they're given our antibody, and we can see immune cell presence. We have taken this context in the clinic, and we launched the clinical trial of this drug. It's the first in the world, and you can see the markers of these patients that shows the tumor growth going down, and you can see the tumor lesions are reduced in the clinical trial. So we have shown that this antibody works even in the patient context in the clinical trial. We were able to publish the work, and it was publicized even on ITV News. We became the news of the day at the time. And I can show you another example here. This is a different type of antibody. It's an antibody that carries a smart warhead, a drug that if you put it on its own, it will kill normal cells, but if you put it on an antibody, it will direct it directly to the cancer cells. And you can see how the tumors are not growing at all when we add our antibody, but the tumors grow happily if we didn't. So we can show that it's possible to restrict the growth of cancer in many different ways, depending on what type of cancer it is and what type of immune response we can study. This is what we try to do. Our vision is to improve outcomes in high-risk melanoma and other solid tumors using antibody immunotherapies that talk to the immune system of the patient, by trying to understand that. And we want to develop a next generation of these drugs that will wipe away the 50% of bad outcomes that we actually see in the clinic right now for melanoma. And we hope we can do that in this place where we can actually, in St. John's, where we actually can interact with clinicians and scientists together and really think about the patient and how we can have a patient-centric therapy and research. And I cannot do any of this without this amazing group. Some of them are here tonight, and I thank them so much for fantastic work. If anybody wants to look at what we do, you're very welcome to scan the QR codes. We also have the study that collects samples that helps us to study the immune response before we can develop treatments. And we use these samples as well to interrogate our novel antibodies there as well. And thank you to so many wonderful people across St. John's and King's and Partners.
Thanks.